Okay, so let's start the lecture then. Today I'm going to talk about click-through rate prediction and research directions, the research topics that we cover at Huawei Research Labs and at Istanbul. I'm going to present for Doğan Dalva. We are working together in the same research lab. I'm working as a senior AI research engineer in the Artificial Intelligence Enablement Department. I will try to check the chat box, or you can ask verbal questions during the lecture, and we will see if there is any question during the lecture. So the contents are as follows. So I'll first mention the definition of the click-through rate and provide examples. I'll talk about some CTR prediction models and what we are conducting as research in this domain as advertisement research project at Huawei. And I will talk about some active research topics and improvements we achieved with these new topics and models. I will mention some industrial applications, and then I will talk about the current status on the digital advertisement market. As we know, click-through rate or percentage of clicked advertisements is the percentage of clicks out of all of the advertisements that are shown to the user. So it's given as a percentage, and PCTR is the predicted CTR. The predictions we have on the CTR. Bias is how we deviate from this actual CTR value. So it's calculated as follows: PCTR minus CTR divided by CTR. It can be negative or positive. Negative meaning that we predicted lower CTR value, or higher meaning that we predicted a higher CTR value. Conversion rate, CVR, is the percentage of purchased items. So actual conversions, purchases that the user conducts after clicking on an item. And we measure the performance using effective cost per mil, so which is obtained by dividing the total revenue by the number of shown events, shown advertisements or impressions, multiplied by 1,000. And this type of predicting CTR enables advertisers to allocate their budget more efficiently. And as there is significant amount of economy around this, it's very important to build effective and efficient and accurate CTR prediction models. And CTR prediction models helps us to identify high-performing ads. High-performing ads meaning that the ads that are very likely to be clicked by the users and engaged by the users. It prevents impression wasting, wasted impressions, and by knowing which ads will be clicked by the users, we will not show those ads that are not likely to be clicked, and we will effectively show only those advertisements that will be clicked by the users, which leads to personalization. Because if we know some information from the user, if our model is able to capture personal information, we can customize and build user-specific advertisements, and we can optimize towards generating more clicks and leading to more conversions in the end. At Huawei, we have different types of advertisements. For instance, splash type advertisements are shown to the user for about 3 to 5 seconds, very short period of time. And banner is when the advertisement is shown at the top of the page of a website as in a banner. And rewarded is when the advertisement is shown after as in a game, so that the users will be expected to finish the watching of the video and then gets rewarded as in a game. So this type of advertisements are typical in or environments. And the features that we use are day of the week, advertisement type, hour of the day, information about the connection used, the network, for instance, and maybe the machine, the computing operating system, pricing information, the pricing of the advertisement or the item that is shown to the user, the age of the user, the gender of the user, previous clicks in the last days. So this type of sequential information is also used. Previous downloads, installs, purchases in the last days, in the last 7 days, 30 days. And we keep this information to predict whether the user will click on this current advertisement or not. And for developing robust and top performing models, we use public CTR prediction datasets. There are two main datasets. The Avazo dataset contains 23 features about the user and the device. And these features includes our website domain and category, device model and type, advertisement banner position. And it contains 32 million training, 4 million validation, and 4 million test instances. The CTR rate is 0.17, so 17% of the instances are clicked. And in criteria dataset, we have 39 features, 13 of them are numeric features, 26 of them are categorical, sparse categorical features. And we have slightly more instances, 37 million training, 4.6 million validation, and 4.6 million test. The CTR rate is higher, 0.26%. This data set is similar to our data, is more similar to our data set that we use in the company at Huawei, because it contains both numeric and categorical features. And its size is larger. Or in our company that said we have about 700 million instances every day, and we process these instances every day. We predict 700 million instances every day about this size. The CTR prediction task involves obtaining user and item features as input, and the dense features and sparse features are divided, and we obtain feature embedding.
Bölüyorum ama kusura bakmayın. Bizde slide ilerlemiyor şu an.
İlerle.
Evet, ilk sayfadayız. Chat'ten yazmıştım ama görmeyince söylemek istedim.
Görmedim, evet. Tamam. Okey. Şey yapayım. Bir dakika. Şimdi gözüküyor değil mi?
Geliyor şu an.
Görünüyor değil mi? Tamam. Tamam. Sayfayı share ettim. Sayfayı share edince farklı sayfa açtı slide'ı açınca. O yüzden farklı şey oldu. Slide'ları paylaşacağım zaten. Bu ilk slide'ları anlattım. Bunlara bakabilirsiniz sonradan. CTR prediction models use sparse and dense features. In neural network modeling, we have feature embedding for the sparse features, and both of these features are combined to the interaction model and used by the interaction model, which tries to generate interesting features like users from Florida who are above 65 years old, so maybe they are retired. So this type of interesting features are tried to be extracted from the data by the interaction module. And interaction module generates new representation that exploits the interactions in the data. And this information is sent to the inference engine, and then this is used by the prediction model to predict whether the user will click on an advertisement or not. We use, as I mentioned, we use public datasets, Avazu and Criteo, and we obtain benchmark results. There is a leaderboard on these datasets and their splits. So there's a specific split of the dataset. There's the specific instances used for the training, validation, and test set. So you cannot randomly use them. You have to use the same split to obtain the same results and compare and make your results comparable. And for instance, in X4 dataset where we have 80% allocated for training, 10% for validation, and 10% for test, we have these benchmark results. So at the bottom, we have different models, CTR prediction models, and on the left we have AUC, and on the right we have log loss. These are performance metrics. We want to decrease log loss and increase AUC. So here, Fibinet model achieves the best result. And we try to keep up with these benchmarking results and pick and select and the best models in order to and implement them in our model database to compare their performance in online results. We have an online system. We have, as I mentioned, we have 700 million instances every day coming and processed by our models. And in Criteo dataset, the sorting and of the models is different. We have DCN model, DCN version 2, and EDCN as top models, and AUC is above 0.81. Before it was less than 0.8, and Criteo results are as follows. In our research lab, we try to build CTR prediction models, CVR prediction models, which is a very similar task, but the models and parameters and their configurations can differ. And we also work on data curation. We gather and store online data sets, user interactions from the online websites, and store them as offline data and run experiments on them. We also perform feature engineering, feature selection, and converting sequential features into a representable format, user features, item features, non-personal, and produce non-personal datasets. Non-personal dataset means personal datasets that doesn't contain personal information. Because of data privacy issues and because we operate in various countries in the world, in Europe, in Asia, Russia, and China, we cannot move data sets out of the region, and we have to respect privacy and data protection measures. Therefore, some data sets doesn't contain personal information. Now, I want to talk about active research improvements. I'll talk first about better prediction models, what type of models we have developed to obtain better CTR prediction models. Then I'll talk about better neural network models, how we improve the neural network performance. Then some techniques for better machine learning, and for a technique for automated research and discovery, how we can build fast models for a given task, and how we cope with large data set size, and how we cope with the bias in the predictions. The first model I want to talk about is FFCP model. FFCP stands for FM, FINT, CrossNet, and PNN model, benefiting from the corresponding layers. It's a combination of the factorization machine for lower order interactions, a deep neural network for high order interactions. FINT model, it's a separate CTR model for field aware interactions, CrossNet layer for higher order explicit interactions, PNN layer for product between embedding layer and the fully connected layer. So these are separate model layers from separate models, and their combination effectively achieves better performance on various data sets. So we built FFCP model. The architecture looks like this. We have sparse features and dense features. Sparse features are transformed into sparse embeddings, which is fed into all of these components we mentioned. IPL is inner product layer, OPL is outer product layer, FINT layer, CrossNet layer, DNN, deep neural networks, and FM layer. And dense features are sent to FINT, CrossNet, and DNN. And the outputs of these layers are concatenated, and then a dense layer is used to combine, merge, and these are added with the FM layer output, and the sigmoid produces the final output. With FFCP, we compare with the component models, and additionally another MassNet model and additional models here in this table. And in our comparison, we observed that FFCP achieves better performance than all of the models compared on the Criteo dataset, and it improves both AUC and F1 and decreases log loss. So it's an effective model. Another technique that we use is residual fusion. We have different models and different types of models, so not necessarily just neural network models for CTR prediction. And for some tasks, some models perform better and some models perform better for some other tasks. And no single prediction model achieves the best performance on all data sets. And we want to combine the strengths of these models for each task. And we know that gradient boosting decision trees are good at modeling dense numeric features. And deep neural networks are good with sparse categorical features. And residual fusion is a technique that combines both of these models in a two-step way. First, we train a model like gradient boosting decision trees, and then the output of this model, GBDT, is subtracted from the actual output, and the residual, the remaining part, is used as the label to train deep neural network. And once we train both of these models, we can add the predictions to obtain the final output. This way, we work on the residual from the remaining part from the first model, and allows us to focus on the hard instances that are hard to predict according to the first model, and which benefits from different capabilities of the learning models, which allows us to benefit from different capabilities of the learning models. Let's say M1 is the first model, M2 is the second model. The pseudocode is as follows. We first fit the first model on the data set. X is the training set, Y is the target, and we predict the M1 model's output on the training set. Y1 hat is the output, and we subtract this output from the actual target, and we also achieve ceiling and flooring operation. Because these are probabilistic predictions from 0 to 1, we make the difference in the same range as the actual output. Residual YRAR is used to fit the second model. So we just only want to learn the remaining part from the first model. using the second model. Then for a given test set, we predict using both of these models, and the final output is obtained by adding these predictions and then bounding to the range. So this way, we are able to achieve performance improvements. So using GBDT as the first model and different GBDT models like GBM or H, hierarchical GBDT, or and the second model as MassNet, DeepFM, as neural network models on Avazu or Kritoy datasets, we achieve improvements that reach 0.85% in AUC and on the Avazu dataset and 0.97% on the Kritoy dataset. And I want to note that 0.1% improvements in AUC are significant and statistically significant. And so we achieved very good results with this type of combination. Another technique is that we can use two different neural networks, because neural network models are also different. Two different neural network CTR prediction models, and they are also good in some data sets, and they have different interaction models, and it's useful to combine them in a residual fusion technique. And we achieve again improvements that reach 0.895 for MassNet in AUC and 0.87 for DeepFM and 0.83% for DeepIM. Another technique is model combination, and we can run several models in parallel and combine their outputs by averaging or another deep neural network at the end that produces the output. This is model combination, and we can experiment with different models here or the same model repeated, because this combination produces more robust results and decreases variance in the predictions. We can also use the same model, since these are probabilistic models. Each one will produce a different result. We can obtain more robust results with a combination like this. The results show that the averaging achieves lower log loss, higher AUC, and lower standard deviation in AUC, so more robust results. And as I mentioned, we can also use the same model repeated 3 times, 4 times with this combination and achieve more robust results. Another technique is extreme learning machines. And we know that single layer feed forward networks are the initial starting point of neural networks, which have only one layer, and the output is obtained by multiplying the inputs x by a weight matrix W and adding bias, and then the activation function G is used, and the final output is obtained by averaging or multiplying with beta weights to obtain the y1, yi, to obtain the output. But this type of gradient-based learning of weights with single layer feed forward networks can cause slow convergence when the learning rate is small. So we know that gradient-based learning can have small steps of learning when learning rate is small, and it can diverge when the learning rate is large, can get stuck in local minima, overfit the training data, and consume time. It can be slow in convergence and slow in training. But there is a benefit of using SLFN, because a theorem shows us that it's a universal approximator. So given an activation function that is infinitely differentiable in any interval, for any randomly chosen weights Wi and Bi, the weight matrix W and bias weights B, we can find a weight beta that will transform the output with probability 1, that will approximate the output with probability 1. So the error will be 0 with probability 1. And the activation functions is not very specific. It's very general, because we can use sigmoid, radial basis, sinus, cosinus, exponential, and many other non-regular functions. So this is a general procedure. And extreme learning machines is based on using SLFN as a learning basis. And it's a ridge regression model with a single layer, as shown in this figure, where weights and biases are randomly initialized as in SLFN. And the W hat and B hat are randomly initialized. Input X is given to the network, and H is obtained with W hat times X plus B, and then an activation function is applied. H is obtained with just a matrix multiplication operation, and W is obtained from the output that obtains the H with a matrix inversion. So matrix multiplication and matrix inversion gives us the extreme learning machine, and there is no back propagation here. And based on SLFN theorem and universal approximation capability of SLFN, ELM is using matrix inversion and matrix multiplication to obtain the output. The way it produces the weight matrix is by matrix inversion, and it can be a regularized matrix inversion as well, to prevent to make the inversion possible for some cases. And the ELM algorithm works with the inputs and randomly assigns hidden node parameters Wi and bias, calculates H, obtains the output weighting matrix by using Moore-Penrose generalized inverse matrix, which is shown here. There are some variants of extreme learning machines. The multi-layer ELM, which has 2 layers, which obtains first W and then WH to model the same, to build a more complex model and with higher precision. So with the 2 layers. And autoencoder is where we try to model the input as the output. So we have the inner layers, hidden layer, as a noise reduction layer, and we try to remodel the input using the and we call this autoencoder, and it encodes the input. It tries to encode itself, and this way we can reduce the noise. And this is another ELM method. And when we apply ELM to the CTR prediction on Avazu and Kritev datasets, we can achieve F1 improvements in F1, but AUC doesn't improve and log loss doesn't improve. This is because the final layer needs to be large for ELM to be more effective. But the benefit of ELM is that it is very fast. So on some tasks, such as digit recognition, it can be fast, 5,000 times faster than neural networks. And in this case, in CTR prediction, it's 3 times faster in our data sets, 3 times faster than other models, CTR prediction models, MassNet models. But it's not performing as good as MassNet. But there is a trade-off. So if you want to achieve a fast model with some close performance to the best model, you can use ELM or multi-layer ELM with embeddings, transforming the input or not, and you can use ELM with for fast experimentation and fast results. So the next topic that I want to talk about is building better neural network models. And the first is instance weighting. Instance weighting is used to build dynamic and adaptive learning to integrate dynamic and adaptive learning in neural network learning. The motivation is that the instances on which a learning algorithm is most undecided can be weighted more during training. So some instances are easy, some instances are hard to learn. And we want the learning algorithm to focus on the difficult instances, hard to learn instances. So to achieve this, we introduced 3 instance weighting algorithms to weight the loss obtained. We adjust the loss with a weighting parameter, and so that the learning gives less weight and less loss to more confident instances, and focus on harder samples while becoming more confident. So it gives more weight to harder instances. To achieve this, we modify the TensorFlow implementation with a WFunc weighting function. And provide that obtains the weight for a given prediction, and this weight, sample weight, is used to update the loss, compiled loss function. The weighting techniques are simple instance weighting, which uses the prediction and the target and weights by the distance to the target, absolute distance. So it gives more weight to more error, to predictions that are more distant from the target. And instance weighting with power takes beta power from this distance error distance, and it gives less weight to instances with more accurate predictions. And the optimizer focuses on hard samples when updating the weights. Instance weighting with distance, the third model, uses the distance from 0.5. So at the initial phases of the learning, the training models tend to produce prediction outputs that are close to 0.5, because we have predictions from 0 to 1. Giving predictions close to 0.5 is a safe prediction, but they are also noisy, and we want to incentivize the model to give predictions that are distant from 0.5. So to achieve this, we incorporate this distance into the weighting function, and we give more less weight to those instances that are distant from 0.5. So 0.5 distant is a threshold that we use in this model. We compared 4 different prediction models and 3 different instance weighting models, and compared the results with cross entropy, CE, and we show in this table significant improvements for all of these instance weighting techniques, and the improvements reached 0.31% for instance weighting, 0.6% for instance weighting with power, and 0.73% for instance weighting with distance in AUC. And the loss is also improved by 2.7% or 2.8% for instance weighting. Another technique is residual connections, and we investigate the integration of residual connections into CTR predictions. I will talk about residual connections in the next slide. And we experiment with MassNet and MassNet enhanced with residual connections. It's a connection in neural networks that improves the performance of deep neural networks. And this way we achieve improvements that reach 0.77% in AUC and 2.8% in loss. Residual connections are skip connections or shortcut connections. Given a model F that transforms the input X to produce the output Y, we add the input to the network as additional input, and so that we don't forget the input. Because in deep neural networks, FX can be very deep. FX can have hundreds of layers. And in this process, the relation with the input can be forgotten. So to prevent forgetting the input, we add this skip connection or residual connection. And this increases the robustness when increasing the depth or the size of the layers. And additionally, as we show in this figure, without skip connections, the optimization surface is very non-convex and very hard to optimize with various local minima. But with skip connections, it's very smooth and it's very easy to optimize, and it converges faster, and we can achieve increased accuracy with increased depth. The dimensions may not match, so we can add a projection matrix WP to the input so that the output, the addition works correctly. And in CTR prediction models, DNN, as I mentioned, produces implicit higher order feature interactions. And FM, for instance, produces explicit feature interactions. But the DNN part can be deep, and so we add skip connection to where the DNN is used in CTR prediction models and demonstrate improvements with MassNet in these results. Here, the architecture is as follows. The MassNet takes sparse features and dense features, which are transformed into embeddings, which are concatenated and sent to layer normalization or by themselves to parallel MassNet layer. And then a DNN is used to transform the input with a dense layer, and a sigmoid is used to obtain the final output. Here we add the residual connection to where the DNN is used, and in a serial connection. So this is serial connection because directly the output of parallel MassNet is used as input to DNN and then to dense layer. And we add a residual connection here. And when we increase the DNN size from 128 to 500 and the number of layers used from 2 to 5, we compare the performance of MassNet with MassNet using a residual connection. And the results show different results. So minus means log loss is decreased, which is what we want, and positive AUC results means AUC is increased, and this is also what we want. F1 is decreased because this is not wanted, but it's not significant. It's a small decrease in F1, but increase in precision and somewhat decrease in recall. Another technique is statistical attention layer. the input given to a neural network can be important, we can have different degrees of importance. And attention mechanism is providing us techniques that allows us to focus on different parts of the input and pay more attention to some parts and pay less attention to some other parts. And for this layer, to develop this statistical attention layer, we use different statistical functions. So mean, maximum, minimum, standard deviation, coefficient of variations, geometric mean, range, root mean square, skewness, and kurtosis. So these statistical functions are used to obtain the attention, and we combine the final output. But how we combine is important, and this is obtained by various experimentation and semantics of these statistics. And when we compare the performance of this statistical attention layer, we achieve improvements that is 0.14% in AUC, 5.43% in log loss, and 1% in F1. The benefit of this layer is that it can be added as a layer to any neural network model and as a processing step, adapting the input, and extends the reach of statistically informed neural network architectures. The way we apply attention is through multiplicative or concatenative techniques. Multiplicative is obtained by just multiplying the input x with weights we obtain from statistical attention layer. Concatenation uses the weights we obtain as additional features and concatenates these to the input. And given Sx representing the statistics obtained on input x, we use a functional form given here in this equation, where W1 and W2 are trainable weights, Sx is the statistics, A is the activation function, and this last symbol is sigmoid function. This type of attention mechanism is referred as soft attention because we use the sigmoid, and this provides us a value from 0 to 1. The TensorFlow representation of these statistical functions are as follows. Here, for the mean, we use the CELU, scaled exponential linear unit activation function, because the mean can take negative values as well. For the max, we use ReLU activation function. For mean, we use CELU. For standard deviation, we use ReLU because it's always positive. And for coefficient of variation, we use CELU. For geometric mean and range and root mean square, we use ReLU. And for skewness and kurtosis, we use CELU activation function. So these are obtained by experimentation. So we compared different activation functions, and this setting achieved the best result. And again, for using various experiments and using the semantics of these statistics, we obtain this formula. So the layer takes these statistics as a parameter selection, as if we are selecting these parameters, and if they are included in the weighting function, they are included as in this formula. So mean and max is summed, mean weight from the minimum is subtracted, and weight from the range is added, and these are divided by the standard deviation and geometric mean weights. And this is depicted in this figure. And we achieve improvements. This table shows improvements comparing the original prediction model and the model after transforming the input with the statistical attention layer. The MMB attention uses only the mean and the max attention. Statistical attention uses 10 different statistical functions and achieves better performance than MMB attention and the baseline model. Relative improvements and improvement percentages are on the right. So another technique we use is better machine learning. So for this, we have developed power loss functions and scaled exponential linear unit activation function. So loss functions are very important in training neural networks and machine learning models. They show where the error is and where we need to improve more, and the learning model needs to improve more. And they are used to obtain the gradient and used in backpropagation in neural networks and to update the weights. And power loss functions decrease the loss for confident predictions and increase the loss for error-prone predictions, just like in instance weighting. So we decrease the loss in confident predictions and increase the loss for error-prone predictions. And they improve both AUC and F1 and produce better calibrated results. We obtain improvements in the results on 4 different classifiers on 2 datasets, and the improvements reach 0.44% for DeepFM on the AWOS dataset. So we use cross entropy in general. This is defined as minus log p for class 1 and minus log 1 minus p for class 0. And p is the prediction, y is the target output. And cross entropy can be depicted as minus log pt, where pt is defined as p when class is 1 and 1 minus p otherwise. A problem with cross entropy is that all instances add to the loss, even if they are easily classified. So when p-value is significantly larger than 0.5, the prediction is close to 1 and it's very confident that it is a class 1 instance. So it's confident, but the error is again added to the loss. Power cross entropy takes beta power of minus log pt, which increases the loss for beta larger than 1 and decreases for beta smaller than 1. And there's another loss function called focal loss, and that has an alpha parameter and also multiplies with 1 minus pt. And we also modify this and obtain power focal loss in this form. So these are power loss functions: power cross entropy PCE and power focal loss PFL. When we plot these, x axis is P and y axis is log loss. The cross entropy is in the red line, and the PCE can have smaller values for confident instances when beta is 0.5, and that somewhat achieves what we want to achieve, because we achieve a smaller loss for confident instances, but at the same time we want to achieve larger cost for noisy or error prone instances, for instances with p less than 0.2, for instance. So for this we use power focal loss PFL, and here we plot the results. The orange and green cross the cross entropy line, and that's what we wanted. So orange, for instance, orange setting with gamma 2.5 and beta 2 achieves smaller error, smaller loss for confident instances, and larger error for error-prone instances. When we obtain the results using these losses, we achieve improvements in AUC and F1 consistently for different models, achieving better performance than cross entropy or focal loss on both Abazu and Criteo datasets, and additionally on the company dataset. So we experimented with PCE and PFL on the company dataset as well, and we achieve improvements. Another technique that we use is the scaled exponential linear unit activation function. So the common activation function used is the sigmoid, and this leads to the vanishing gradient problem. So with deep neural networks, the gradient becomes smaller and smaller, and which doesn't affect the weights in deep parts of the network. To prevent the vanishing gradient problem, the activation function is changed to ReLU, and which takes the maximum of input x and 0. This is useful, but we also need the negative slope, as I mentioned, in the statistical activation layer, where we can have negative values. The activation function that is also using the negative values is beneficial to the learning. And PReLU is parametric ReLU and allows negative values, which is another activation function. Exponential linear unit is also another activation function that allows negative values, which is given at the bottom right. And scaled exponential linear unit is multiplies exponential linear unit ELU with S, where S is larger than 0. Using CELU activation function, we obtain self-normalizing neural networks because it is found that the neuron activations converge towards zero mean and unit variance. So this means that we don't need to use normalization, batch normalization, to convert the mean and the variance. Because in deep neural networks, the mean and the variance can also increase, decrease, and we want to normalize them to unit variance and zero mean. But using CELU, we don't need to do that, and we don't need to use batch normalization. And this allows us to train deep neural networks with many layers and to make learning highly robust. When we obtain results for different number of layers in the DNN, when we increase the depth, and the performance improvements are shown in these figures. For DeepFM, the log loss decreased by 8% up to 8%, and F1 increase, and AUC doesn't change much, and MassNet for DeepFM CELU improves the results, and for MassNet PReLU improves the results. And so changing the activation function using CELU activation function improves the results, and for CTR prediction. Another technique is automated research and discovery. So as I mentioned, CTR predictions use different interaction models and that try to learn interesting interactions, interesting combinations of features to extract more information. So extract information that is relevant to the task. And over the years, various interaction modules have been developed. So we have hundreds of different models. Each is using different types of interactions, and some are better in some datasets and some are better in another dataset. And for instance, DeepFM takes inner product of two feature vectors, and PNN uses the outer product, and they both consider only second order interactions, but DCN model uses higher order interactions as well. But it takes years to develop these models, and various experiments are required to develop these models. And with interaction construction machine, our goal is to benefit from this previous research, previous interaction models, and develop a technique that can combine the useful parts of these interaction models to develop an automatic model building architecture construction machine that can find models in hours, that can develop new models in hours. So as I mentioned, the debugging and building new CTR prediction models require expert knowledge in the field and takes significant resources, man hours, and technological advancements. And additionally, these new designs can be not very useful when the dataset changes and the, for instance, the online result and the traffic changes. So we instead we can use these interaction models concurrently and consider more complex architectures, combining the beneficial parts of these together to achieve better performance on a given specific dataset. So we can build a new model for a given dataset and task on the fly and as datasets come. Interaction construction machines uses previous set of interaction modules, their code and implementation, and searches for the best selection. Given a selection of these interaction modules, which are binary selections, so either selected or not, and this leads to an exponential number of possibilities for a given number of interaction modules. But we can use effective search techniques to find new models in a couple of hours and construct the instruction construction machine ICM. Given this selection, constructs a new model, then evaluates on the development set and repeats this for k times, and then outputs the best model. It's a architecture search machine. So these are called neural architecture search machines, and um, it's part of this category, neural architecture search. The results on different datasets are shown here. On the Avazu dataset, we achieve improvements compared with other models, component models, and other best models. Again, we achieve improvements on the criteria datasets using ICM M2 model. The improvements reach 0.26% in AUC, 0.43% in logos, and 1.8% in terms of F1. And on the company dataset, we achieve again improvements on Huawei datasets. The architectures are shown like this, and ICM M1 dataset is on the left and M2 dataset is on the right. So different architectures are obtained for different datasets. Another technique that we use for coping with large dataset size is sampling. As I mentioned, we can have billions or hundreds of millions instances per second for a day, and tens of millions per second, and or millions per second. And we present efficient downsampling techniques to sample CTR prediction datasets for faster training with limited decrease in the performance. So we want to decrease the performance, decrease the dataset size without decrease in the performance. And as we know, we are trying to predict either 1 or 0, or clicks or not. And most of the dataset is not clicked. So because CTR rate is 0.17, for instance, in Avazu, 17% is only clicked. And in our datasets, it's about 8%, 6%. And so 94% of the dataset is zeros and not clicked. So it's not very useful to use all of this non-clicked information. So it's better to sample from this data set. For this, we use feather files, so which are used to store data sets into different into a portable format, and the data set is split into multiple batch size feather files, and then the data is read from these. But this is not very efficient because reading from the file takes computational and hardware resources, hardware resources, energy, and time. So we developed efficient sampling, which we input a sampling rate from 0 to 1, maybe 0.05, for instance, 5%, or 50%, 25%, which multiplies by the number of feather files and obtain L. And then we shuffle all of the feather files, all of the data files, and from 1 to L, for the number of data files we want to read, we read the instances from these sampled data files and concatenate them to obtain a larger data set. And then we shuffle the indexes. When we look at the results, we observe that up to 25% of sampling, so using only the 25%, the performance doesn't decrease and even increase. The F1 results and recall results are increased. But with 10% sampling, discarding 90% of data, the performance starts decreasing. Another technique we use is coping with bias in the predictions, because the test set data set is different from the training data set, and their distributions are different. And when we fit the training set, we can overfit, and the distributions we obtain, the p-CTR values, the predicted CTR values, can differ from CTR values on the test set. And calibration methods use validation set or training set that match, that are close to the test set, that whose distribution is close to the test set, to calibrate the results. So they build another machine learning model on top of the predictions to adjust the prediction means, to adjust the predictions and scale them towards actual CTR values so that the bias is decreased. So as I mentioned, there can be differences in the distributions of the CTR values in the training set, validation set, and test set. And the p-CTR is also can also be different. And so our goal is to make the p-CTR distribution close to the CTR, close to the test set CTR. We can use different loss functions, 3 different loss functions for these experiments. Focal loss and L1 regularized cross entropy are known to produce calibrated results. So we compare with cross entropy. And we have 5 different calibration techniques: isotonic regression, plots, scaling, neural networks, spline regression, temperature scaling. And we experiment with all of these techniques. So on the top is cross entropy loss, but middle is focal loss, and lower is cross entropy with L1 loss, L1 regularization. And we experiment with all of these 5 different calibration techniques, and we achieve improvements in loss, Briere in expected calibration error scores. These are scores to evaluate the error and the calibration efficiency, and we achieve improvements in all of these metrics. And when we look at the differences, the neural network model, which we developed, and other methods were in the literature, but the neural network model decreases the expected calibration error the most, but it's the slowest. But and when we compare the trade-offs, about 600 seconds can be manageable, acceptable when we consider 12 hours of training data sets. So 600 seconds is 10 minutes compared with 12 hours of training. It's negligible. And but comparing the differences in the loss and AUC and F1, isotonic regression achieves good results with this fastest technique among these calibration techniques that we compared. And I want to talk about the applications we use for CTR prediction. And one of them is Huawei App Gallery, where the users uh, install an application and browse applications. We have advertisements here, and we have also developed a book recommendation for universities, where university libraries can use our technique to recommend books to the users. And I want to remind that we have about 1 billion views and CTR predictions every day with these type of models. And digital advertisement market is increasing, so the revenues and the budgets are increasing every year, and it's expected to grow 16% annually from 2023 to 2030, and it's expected to reach 750 billion US dollars in 2030. And as we know, online competing companies like Facebook and Google has most of their revenues coming from digital advertisement, and Facebook has the revenue. 99% of the revenue comes from digital advertisement of Facebook, and 92% of the revenue from Google is coming from digital advertisement. So it's a growing market, and it's a significant market. Thank you for listening. So these are the topics that I wanted to cover for today. If there is any questions, I can try to answer. Otherwise, we can end the session. And thank you for attending the class. I will try to ask a question from these slides. Hopefully you enjoyed the class. Thank you. Bye bye. Hoşça kalın.